Okay, so we've got a couple different formulas that we're going to use. And the first one of those is if we want to do an addition. So we've got 2 points, x1, y1, and x2, y2. And we want to add those two together to find x3, y3. And our formulas work like this. If the 2 points are different from each other, then we're basically just using the point slope to find it. And that's this first formula up here. Easy to calculate, a very little bit of algebra. And if the points are the same, that's where the points match, then we've taken the derivative, we factored it out, we've put it all on the other side, and we've gotten this other formula over here. So there's the formulas for calculating it. And all you have to do is just calculate out the points. Then if you're multiplying, you do this other thing with shifting and doubling. And every time you double, you're using this point formula here. When you get done, you do a bunch of adds down here. Now, there is some reasons why on some elliptic curves, your adds come out to be a double of the original point. Okay, whatever that is, don't worry about that. Just check the points. If they match, you just double as opposed to add. And you add them up and you can multiply. So that's fairly simple, fairly straightforward, and that's how it works when you have continuous values. Now, with discrete values, it turns out, that's all floating point. With discrete values, it turns out it still works the same. We can build these sets with discrete values. And I want to show you, first of all, a little detail about this. Now, part of what we get with discrete values is we're going to do the Space Invaders thing. When it runs off the edge, it comes and wraps back around. But if you look at the discrete values in integers, and I've changed my range from 4 to 30 here. So I've got from 0 up to actually 31 as a prime in each direction. But I think if you look at this, you'll see that this funny line that I'm connecting right here is my elliptic curve. And I've chosen this because it shows up pretty nicely. And then we get these other points that are the result of our modulo division, which is our elliptic curve again, coming around, and some other points over here. But this set of points that we have when we use it as integers makes this elliptic curve work. And every one of the mathematical calculations can now be done on integers, and it always leads to another point. Now, one of those magics of picking the P256 or the ED25519 curve is that there are enough of these points. And that's actually the hard part, where you have to try different curves and do some calculation. How many points are there when it's discrete? And the magic of the predefined curves is that they have picked versions of these curves that have at least 2 to the 128 points. So it's 2 to the 256 is the total possible range. That's the outside of the box here where we wrap around. But the number of points inside is greater than 2 to the 128. And 2 to the 128 corresponds to the strength of 128-bit encryption, not public key, but the encryption standard. So that is enough points that if you do a digital signature on it, you're not weakening other encryption. So that's the magic of the picking of the curves. And there's some math that we don't want to get into. It's icky. How they got there and why they picked the curves they did. But underneath the covers, that's the reasoning behind it and what you want for curves. So when we go from floating point to integers, we end up with points. All the calculation always comes back as an integer, and we can still work with this set of values as integers, and there's plenty of them. So if we look at an elliptic curve where we want some point A over here, and this is all discrete, added to some point B, we draw the line calculating the slope, and we go zooming off. In this case, we zoomed off right here at this edge, and we wrapped around to here. That's the modulo division. We zoom off over here and we wrapped around to here, and we're looking for when we hit another point. We zoom off here and we come over here to the other side where we come back on and we go zooming down, and finally we hit this point right here. We take the corresponding point on the other side, reflected around the axis, and that gives us a point over here. And that's the sum of a plus b. And since we know something about all of these lines, that they will always intersect another point, we're guaranteed that we always have a result that allows us to do this. Now, the nice thing about modulo calculations in this is because our space is finite and everything wraps, none of our numbers ever grow. And this is the big thing about the difference between elliptic curve and RSA public key. Is in RSA public key, we don't have this modulo operation going on. And consequently, the bigger the keys get, the bigger the calculation gets, the harder it is to do. So as computers get faster, we can use bigger and bigger calculations, but that also means that the amount of data we have to transfer in every calculation grows. It's not fixed. And that growth doesn't get us any more security. It's that we have to make the calculations so we can't turn around and factor these smaller numbers because computers and algorithms have gotten better. When I started out with RSA cryptography 30 years ago, 100-digit decimal was plenty of security. That was considered high security. Today, my RSA keys are the small ones 4K, the big ones 16K, and I'm looking at 32K long numbers, 32,000 digits to provide adequate security. And it doesn't give me any better security than 256-bit elliptic curve. What it does is, it prevents these other attacks from happening because computers have gotten faster and factoring has gotten faster. So most people that are working with this stuff like the elliptic curve things because they're fixed and they provide the same security, but they do it with this modulo thing built in so that the numbers don't get bigger over time. And if you want more security, you go to a bigger field, but your field still is fixed in size and everything wraps. The other advantage of the modulo arithmetic is that we have really good, fast, large number calculations and exponentiation that works with modulo arithmetic. And because of some things that I quite frankly don't understand and haven't taken the time to sit down with the algebra, this ability to exponentiate modulo some value is really rather quick, as opposed to doing an exponential calculation and it growing exponentially in size. It works out and it's relatively fast. So there are plenty of these things that are fast and the data size doesn't grow and it still works with integers. So lots of good reasons why elliptic curve is being used for 85% of all of the TLS keys and public key cryptography stuff in the world today. And I'm taking that number from, I did some work with Let's Encrypt, which is free public keys for SSH and HTTPS, the TLS transport layer underneath that. And we can look at the logs and we can see the number of times that those keys are elliptic curve and not. And most of them today are elliptic curve over most of the entire World Wide Web. So this is the one that's being used. That doesn't mean that there aren't things that you'd still use RSA for and it has some other properties. It's just much slower and much harder to do.